Hello, everyone. Thank you for coming. So my name is Ivana Scala. I'm a graduate student here in the astronomy department, and I'll be the lecture captain for tonight. So the structure of our program is it's composed of 30 minutes of a lecture, which will be given by Matt Orr tonight, and followed by 90 minutes of a question and answer panel with a number of postdocs as well as graduate students here at the Cahill Center for Astrophysics, and also 90 minutes of telescope observing. So I would like to emphasize that you can move back and forth between the panel and the question and answer session, and the stargazing session after the lecture is actually over. So the observing status for tonight is pretty clear, although it is very windy and not very warm outside. So the targets we'll be looking at for tonight are the Pleiades, the Moon, which is very bright as it is usually, and the Orion constellation. So as you entered, you may have noticed the swag that we have outside for you. Please feel free to take it. If you see the survey, please fill it out. It gives us valuable information about why you're interested in astronomy and what your background is. We also have information about the next upcoming lecture series over there. So I would like to remind you that while you're outside on the field, that there is no food, drinks, smoking, pets, or high heels, just because we can't damage the AstroTurf or whatever out there, because the athletics department will get mad at us and will not let us have this stargazing and lecture series again. So there are a number of signs outside that are glowing brightly that will direct you toward the stargazing area on the field. So it shouldn't be too hard to find it. You can identify volunteers by our badges, and they flash very nicely like this. So it also shouldn't be hard to find us. So our next upcoming events that we have are Sidewalk Astronomy tomorrow. So you may see a bunch of astronomers out with telescopes in Old Town. We also have our Astro on Tap events, which are held at a local bar called Der Wulfskopf, where you can listen to informal talks on astronomy while also drinking beer. So unfortunately, this is not an event for the children. And our next lecture is on March 23rd, and it's called The Truth About Black Holes. So that one should be pretty interesting. So our lecturer today is Matt Orr, as I said earlier. He is a fourth-year graduate student and NSF Graduate Research Fellow in Theoretical Astrophysics here at Caltech. So the fancy name for the whole thing is TAPIR, which stands for Theoretical Astrophysics, including Relativity. And their mascot is an actual tapir, which is very cute. Matt studies galaxy evolution and star formation in cosmological simulations. He hails from Southern California and has never really left the Los Angeles area, and has grown up in the shadow of NASA's Jet Propulsion Laboratory. So as an undergraduate at the University of California, he studied physics, minoring in astronomy, and also conducting research in astronautical engineering. So you can feel free to ask Matt about amateur rocketry later, but today he'll be talking to us about a subject that's integral to his thesis research, which is why galaxies aren't great at making stars.
Hello? All right. So thank you all for coming out tonight. And again, to illustrate, we don't have a live tape here. There is no harm of animals in this building. So I'm here to talk to you guys about galaxies today and why they're just not good at the one thing they're supposed to do. So again, name's Matt Orr, and I'm a graduate student up on the third floor here. So I'm very excited to tell you guys, oh, wow, that got really cut off. All right, that's what this is going to be. Okay, so we're going to learn about star formation today. And in this foreground here, we have a really beautiful image from the Hubble Observatory. It's of the Tadpole Nebula. So what you're looking at here is a big cloud of dust and gas where young stars are forming, sort of as we speak. And it's called the Tadpole Nebula because there are these little tadpole-like figures in them. And now, they look kind of small, but they're really 10 light years across. So this is a very big image, and the whole thing is about 100 light years across. So in this big region, we can see sort of all the interesting, crazy stuff that's happening when stars are forming. We have, bright, hot young stars. We have big, cloudy nebula, and all these pretty pictures that might be the backgrounds of your MacBook Pros or what have you. So the questions we're going to try to answer tonight are, where does it happen? Where does star formation happen? And why does it happen? So this one wasn't cut off. Stars forming galaxies. You know, if you guys had to leave early tonight, you could take this home with you. Stars forming galaxies, they're in these pretty, you know, spirally, beautiful structures that look a lot like a Milky Way bar or something like that. And the question you might then ask is, well, what are galaxies? You just told me galaxies are where stars form, and they're these pretty beautiful things. Aren't they just a bunch of stars? And yeah, you know, they kind of are. It's just galaxies, by definition, are big groupings of stars. And back in the 20s, we finally figured out that there were all these other groupings of stars out there, and so we had all these different galaxies. Now, there's other stuff too, which is the important thing that we need to take away tonight when we're talking about galaxies. Well, what else is in them? We have gas in galaxies, which all I care about is that it turns into stars. It's the fuel for star formation. And it's also all the pretty colors that we see in these galaxies, because we have the starlight, which is sort of the yellow stuff, but in this image we have these blues and reds, and they're sort of fake images, because if you just look out at a galaxy, you know, through the telescopes tonight, you're going to see these nice sort of blurry, kind of pretty blue clouds. If we were looking at, we were to look at the Andromeda Nebula or what have you. But for us humans with our eyes that aren't cameras, we just get these smears. But for things like the Hubble telescope, we have these beautiful spiral nebula. So there's all sorts of other stuff in there too. There's dark matter, which was cut off from this image, which is kind of fitting because for what I study, it doesn't really matter what dark matter is. It's heavy, and it's there, and that's about all I need to know. And that's about all that stars need to know for star formation and gas and stuff. And there's planets. Earth's cool. We live on a planet, so planets are pretty near and dear to all of our hearts. But for star formation, we don't really care about planets, which is kind of an interesting thing in and of itself. So, top this says, the defining feature of galaxies are stars. So the important thing about galaxies is that it is a collection of stars. One of the old archaic definitions of what a galaxy is just a collection of bright individuals, which you can see the parallels to stars. And as a result, that's really all we're talking about when we talk about a galaxy. And until 1915 or so, when we said galaxy, we just meant the Milky Way. You know, you're camping out in Joshua Tree or something, you see the band across the sky, and that's our own home that we live inside of. But turns out there are all these other, there's this big blob in the foreground, which is a big galaxy full of stars that doesn't have a lot of structure. And in the background, there's another nice spiral galaxy kind of face on, and you can't really see a whole lot of other things in this image. So this foreground one is something called an elliptical galaxy. It's just kind of a blob. And we have another spiral, and throughout it, there are these little dots. They're just stars from our own Milky Way. And it took until the beginning of the last century to realize that all these other things out there weren't just clouds, beautiful clouds in our own Milky Way. We didn't know that there were other galaxies out there. And indeed, when we first figured out that these things were so far away, they were much further away than any other stars that we could measure in our own Milky Way, they first called them island universes. And they thought that, okay, well, we live in our own island universe. There are all these other island universes out there. And after several drinks at a couple of conferences in the 20s, everyone settled on galaxy. They're all galaxies. We live in a galaxy, and those other things are also galaxies. But it took until the mid-1920s and the 1930s for us to really realize that, well, the Milky Way is not so special. And it was kind of one of the first, the last steps in this thing called the Copernican principle, where in the 1500s we said, okay, well, the Earth's not at the center of the solar system. The sun is. And then we said, well, okay, we can see out in our own galaxy that the sun isn't all that special compared to all these other stars. So the sun's not all that special in the galaxy. And then once we discovered there are all these other galaxies out there, well, our own Milky Way isn't all that special either. It's one of hundreds of millions, if not billions, of galaxies out there in the observable universe. And so we might start asking more questions about, well, what makes all these galaxies special? Why is the Milky Way, when we look up and see in the night sky that nice band across it, why do we see that in our own Milky Way? Turns out a lot of this depends on how massive these galaxies are. This big elliptical galaxy is something like 10 times as big as this spiral galaxy in terms of if you put it on a bathroom scale. And so you start wondering if you can ask questions about the populations of galaxies. I really should have checked all my slides. The first question you might ask is, well, how many galaxies are there that are big? How many galaxies are there that are small? Is there a relationship between the number of galaxies and their sizes? And indeed, there is. It's something that all of us astronomers love to call the galaxy mass function. So what matters here is how big are the galaxies, so bigger things that way, and how many of them are there, so more things up here. And as it turns out, there are a lot more smaller galaxies than big ones. Yeah, it kind of makes sense. And then we live, the Milky Way is kind of special in an interesting way. It's right at this knee here, where we're the biggest of there's a lot of us galaxies. And so the galaxies on the left, these smaller ones, turns out they're mostly they're these beautiful spirals that you have on your backgrounds of your laptops and things like that, or we paste all over the front of our building. And at the other end, we have these big blobby things. And these big blobby things, I don't care as much about. We call them elliptical galaxies or irregular galaxies. And there's no star formation in them. They're just big, dead blobs of stars, as far as I'm concerned. And so a lot of astronomers will call them red and dead, because they're red in appearance and they're not doing anything. So we're going to talk tonight a lot more about these spirally beautiful things. So turns out the shape of this, why there are so many galaxies of a certain size, is because these galaxies have just been turning gas into stars since the beginning of time. So over time, things start out small, and they start building up more and more stuff. And the first galaxies that turn on and start making stars, well, they're the ones that are going to get out to the front of the line before we run down the clock 14 billion years to today. And we're one of the leaders. The Milky Way is number one in terms of star-forming galaxies. Now, these big blobby galaxies are, in fact, when smaller galaxies just collide. And when they collide, they blow all the gas away, and they just stop doing anything. And so it's through this process of merging that you make bigger ones. And they're much, much rarer, because you'd imagine if you have to go over to your neighbor's house to ask for a cup of sugar, you're not going to do it that often. And if your neighbor's house, if you live out in the sticks and your neighbor's house is a couple 100 million light years away, you're not going to go over to your neighbor's house that often. So it's pretty rare that two Milky Way mass galaxies will combine to make a galaxy twice as big. And it's rarer yet that two twice as big as Milky Way galaxies find each other and slam and make an even bigger one. So we get very few really big galaxies. And that's why it's exponentially rare. So again, we're just going to talk about the small ones. So we care about galaxies because that's where stars form. I personally love spiral galaxies. There are smaller ones that aren't spirals, but spirals are really pretty, so we're going to talk about those a lot. And they're star-forming. So it's small star-forming galaxies, which is what make up the bulk of the galaxies out there in the universe. So the top that says, what's happening in star-forming galaxies? Why are they forming stars? Or why are stars forming in them? We have so many of these pretty images of these beautiful spiral arms, which all these little purple points in them that aren't, these are stars in our own Milky Way, or very distant galaxies. All these little purple things are where stars are forming. You're looking at the envelopes of really hot gas that are surrounding young stars, that are harkening back to that first slide that I showed you. So making stars, a simple recipe. You take stuff, and gravity turns it into stars. It's as easy as it is. And it turns out, though, that, again, it's a lot more complicated than that, because if it was just gravity turning stuff into stars, you'd think, oh, well, the universe is going to be full of nice little spheres that collapse, and then a light bulb just flicks on, and we have stars. Instead, it's this horrible mess, which is great for me because I still have a job and everyone didn't figure it out already. But we have young stars that are forming in the middle of this thing, and as soon as they start forming, they're blowing apart the cloud, and it's a horrible mess because these young stars have bright UV rays, and there's X-rays coming out of them, and they're blowing winds off, and they're tearing apart the clouds that they're forming out of. And eventually some of them explode even and blow the whole thing apart, so they're ruining it for everyone. And this is a process that we call feedback. In the background here, there's another famous picture that some of you might recognize. It's the Carina Nebula. And this whole thing is, I think it's 3 or 5 light years long, so pretty big thing. And there are some bright stars here and some stars off screen that are blowing this cloud apart. And in only about 100,000 years, this whole cloud is just going to evaporate. And this is, hundreds or thousands of times the mass of our own sun, and it's just being blown apart by these other young stars. So, they're playground bullies and kind of keeping all this stuff from growing and turning into stars itself. And that's this process that we try to understand as the gas cycle. Now, those of you who are closer to elementary school might remember the water cycle, and you're being taught that. And, water comes out of the ocean, rains on us in California every once in a while, and goes back into the sea. Very important for us. And the gas cycle is a similar thing for stars. So if you start out with a big blob of gas way out there in the universe somewhere, And you're like, okay, well, what's gravity going to do to me? Gravity is going to make me break up and start collapsing and turning into little subclumps in my cloud. So you have a big, nice thing, and gravity immediately turns it into a mess. And those little clumps are going to start getting denser and denser and colder until somewhere in them, stars form. So, the densest thing is going to collapse the quickest because it has the strongest gravity. And in those little pockets, you'll get your first set of stars. And as soon as those stars form, their hot, bright light will start ruining the situation for all the other forming stars. And so they'll start blowing the cloud apart. And as that happens, the cloud breaks up. It's supposed to be a broken heart up there. It's a fun little visual joke. But anyways, the cloud breaks up, and some of the stars explode. And sort of the end of star formation happens when the first star explodes in the clouds. So you have, from here till a lifetime of a star to make stars. And the biggest stars burn up their fuel the fastest and live for only a few million years. All right, it's a very different time scale than between now and lunch, but it's really short in terms of how long the galaxy takes to go around and how long our own sun has lived. Since our sun is 4.5 billion years old and it's still kicking, it's got another 4.5 billion years to go. But stars 10 times, 20 times the mass of our sun will only live 10 million years. So very short time scales. And then you wait a while and gravity does its thing and it'll reassemble these fragments, or new stuff will fall in the galaxy, and you'll make another big blob of gas, and the whole process will start over. So lots of people will argue about it. There's some people in this room with very strong opinions about how long clouds live for. But the idea is it's somewhere between 20 and 100 million years you have to go from the beginning to the cloud explodes and you dump some new stars into the galaxy. And this other part of it takes probably about as long. So together it's between 50 and 100 million, 200 million years between star formation events, if you're just following some little orbit around the galaxy. And interestingly enough, this is almost exactly how long it takes to go around the galaxy once. So sort of coincidentally, it's basically for every cycle, every revolution of our pinwheel of the Milky Way, we get a batch of stars, which really means that only a small fraction of gas and dust and stuff is turned into stars every time it goes around. So galaxies are pretty bad at making stars because if this explodes and you have all this stuff left over, well, you haven't turned all of it into stars. So as a result, galaxies are really bad at making stars. And only a little bit gets burned up every time it goes around. So, you get a couple percent every cycle. So how can we tell this is happening? How do we know how many stars are made in a galaxy, per orbit or just every once in a while? This is what I study. You're lucky because I'm here tonight to tell you all about it. So we're going to talk about something called the Koenig-Schmidt relation. Now, I'm just throwing another figure at you because I really like this one since unlike a lot of other laws in science, the people who came up with it are both still alive. It's kind of rare these days. Rob Koenig is a professor at Cambridge in jolly old England, and Martin Schmidt is actually a professor here at Caltech. He lives just right down the street. And he was on the cover of Time magazine in 1966, so he's getting up there in age. But he still eats lunch every day, and there's a great book about some of the work he did at Caltech in the 60s, 70s, and 80s, and it's a great read. I don't get any royalties, but it's a great cover of Time magazine. So this tells us how bad, this Koenig-Schmidt relation, tells us how bad galaxies are at making stars. So on the bottom, we have how much stuff is in galaxies, so more stuff this way, and how many stars that stuff is making along this axis. So up here, a lot of stuff, making a lot of stars. Down here, not too much stuff, making not too many stars. Now, these dotted lines that have been added for clarity are basically what percentage of stuff gets turned into stars on every orbit around a galaxy. So as you can see, 1%, 10%, 100%, nothing except maybe that thing is turning all of its stuff into stars in an orbit. So you can kind of see right off the bat that it's maybe 10% efficient for almost everything, which is way worse than most batting pitchers are at batting. So that's giving you an idea of just how bad they are at their job. So the things down here, they're out in the boonies. These galaxies don't have much stuff in them at all. They're terrible at their job. They're very, very bad at making stars. It's a couple percent every time they go around. In the middle, they're kind of bad. You're maybe pushing 10%. That's pretty good for a galaxy. And then some of these things up there are much better. They're in the tens of percents. Maybe a third of your stuff turns into stars in an orbit. And these are really extreme objects. Down here, we have like thousands of galaxies and parts of galaxies that we've looked at. And up here, you can see all the points, and there's like 20 of them. There are 20 really star-forming galaxies. So part of the question is maybe, it's cut off, but better maybe, because we don't have a lot of data, and we're not really sure. But they're better, but they're all garbage. And so if we look at one of these, this beautiful spiral galaxy before, we can kind of point out where these regions are. So the center of the galaxies, it seems like the most gas-rich, where there's most going on, is right in the middle of the galaxy. So that's where you might be hitting tens of % efficiency in your star formation. And it's so star-forming, in fact, that as the star formation happens, so many stars form before the first star is able to explode that they kind of go through these breathing modes where they make way too many stars, and then all those stars kind of blow up at the same time, so they blow out all the gas, and that gas all falls back down in the middle of the galaxies, and then blows it apart again. So they're really violent, messy things. Then when you get out to the suburbs of your galaxies, you're sort of right in the middle class of your star formation. That's kind of like where we live. And then way out in the boonies, there's not very much gas, and there's not very many stars forming. So it's not super great to live out there. And we kind of live sort of the outer edge of the suburbs of a galaxy, of our own Milky Way. So if this was us, we'd be kind of out there. Still a nice place, but some people have like cows and stuff. There's not much going on. So how do I study this? I work with simulations. So in the background here, we have one of the simulations I work with. It's a Milky Way mass galaxy today, or it would be today. And we're looking at all the starlight of the galaxy as it forms its stars. So in the center is where the galaxy is going to live and be. And you can see all these other little nuggets coming in. And way in the early parts of the history of the universe, it was not a nice place to live because you have other galaxies slamming into your own all the time. Because there's lots of tiny neighbors that decide, I want to live over there. And so they all kind of fall in by gravity to make a Milky Way. Because we can't do it alone, so to speak. And so we need all these neighbors to come on over and help build up our galaxy. And so over time, gas falls in from very far away as the galaxy is forming through time, and tiny, smaller galaxies are falling in all the time. And this particular simulation kind of works like our own Milky Way, except a little bit sooner, where the Andromeda Galaxy, which many of you might have, if you own a MacBook, the background is probably the Andromeda Galaxy, and it is falling in towards the Milky Way. And in a few billion years, the Andromeda Galaxy is going to slam into our own, and we're going to double in size, and it's going to be great. And this galaxy, well, I guess star formation will turn off, so it won't be as much fun. But this galaxy has a big neighbor come on over right as the simulation ends. So it's kind of a tease because they don't actually hit each other. They get really close, and the simulation ends. We could run it forward, but I guess we ran out of time on the computer. So there it goes. It goes out, and then it's about to fall in, and you're like, oh, it's going to happen. I didn't time it right. And then it's about to fall. There we go. And then the simulation is over. So it's really terrible. The cool part about these simulations is that we get to look at them in a lot of different ways. Because when we're looking out there in the real universe, one of the problems we have is we have just one picture of a galaxy for basically a human lifetime. We get to see it in a snapshot of whatever it's doing right now. But it's kind of nice with the simulations. We get to watch it through all of time. And we get to see, what's a baby galaxy like? What's a little bit older galaxy like? What's a galaxy today look like? And so on the left, we have the starlight, which I just showed you. And on the right, we have all the gas in the galaxy. So the green is the dense, cold gas where stars are forming in. The red is this hot gas that's kind of out in the environment around it. You can see all these little, and this one's zoomed out a lot. So like this little bar bit is this whole thing. And you can see like all the other stuff coming in. And so it's really cool because we get to look at it. We have all this extra, we can look at it in all these ways that it's much harder for observers to do. And that's the fun of being a simulator, because we get to play God with our galaxies. So I get to make things like this where I have one galaxy, and I'm looking at it as though I have a telescope, but I get to take lots of pictures of it throughout its time. So I get to know, are the galaxies exploding? Is it special right now, or is nothing happening, but I'm kind of being tricked? So I get to I'm trying to translate between these simulations and observations. So I'm trying to build a bridge between them, which is really neat because simulations are very unique in this way that we get 100 pictures of a galaxy instead of one. So to conclude, everything got cut off on this one. Just remember, if there's nothing else you take away tonight, galaxies are just big star factories. They do nothing but turn stuff into stars, and then they're pretty, so that's nice. And all the gas in them are stuck in this vicious cycle of stars are forming, stars are exploding. Stars are forming, stars are exploding. And so they can never break out of it until someone comes over and just knocks them out cold. And even though they're stuck in that, they're terrible at the one job they have. And I'm terrible at making slides because everything got cut off. But galaxies are just awful at making stars. And as a result, thank you for coming out, because even these terrible slides got you to come out tonight. And I'm supported by all of you, so thank you for supporting me in a very convoluted way. Thank you for coming out tonight.
Okay, so we have time for a few questions for our speaker.
Hi. How do black holes fit into this? I mean, as far as formation of stars, especially when you mentioned the center of the galaxy. And what about giant black holes? How would that affect it one way or the other?
So the centers of galaxies and the massive black holes in them are a really interesting area where stars are forming, because their gravity is super strong, so the orbits of bits of gas and stars around them are very fast, and it drives a lot of turbulence, we think, where these are particularly messy environments. Now, for a galaxy, let me just go back to one of the pictures I have somewhere. For like this galaxy, it would only be this like a very tiny little area around it where we think that the black hole is really affecting how chunks of gas and stuff explode or blow up. But we think that they're particularly on-off, very efficient or very inefficient at making stars, because the turbulence either suppresses the fragmentation, but under the right conditions, it kind of forces all the stuff to turn into stars in a very short amount of time. So it's a very interesting, weird area to look into. So people study it all the time. There's a postdoc in our group that looks at it. So the simulations, we do our best to put in as much physics as we can until the computer says this is hard and going to take forever. And so we try to, we put in gravity, we put in young stars are really bright, old stars aren't as bright, gas turns into stars. Gas turns into stars only when it's dense. Gas is hot, gas is cold, based on putting in as much like thermodynamics as we can. So we just try to cram in as many rules of physics that we know of that we think are important. Because you can leave out stuff that, maybe you don't think it's important, so you leave out a particular way that old stars might be weird because you don't think that's important. So we just try to cram in everything we can, and we just put it on a computer and say, all right, go to town, I'm going to get coffee.
First, I just have to say it was fascinating to watch these forming and collapsing repeatedly in your simulation. I love that. Two simple questions. First, you mentioned that these gases are cooling as they, well, actually before that, how hot are these gases that are glowing before they form stars, roughly?
So in, for instance, in this image where there's the little knots of pink.
We've seen these glow in visible light, right?
So that's in infrared. Most of that's in infrared, or in the red end of the spectrum.
So how warm are they?
It's all about 10,000 degrees Kelvin. So it's quite warm. It's the temperature at which hydrogen is losing and getting back its outermost electron. So all these temperatures are kind of set by that, where galaxies can cool down really quick until everything is neutral, and it kind of sits there for a while. And then once you can make molecules, you cool off really, really quickly. And so a lot of stuff is stuck either at very high, at these high temperatures of like 10,000 degrees, or they cool off rapidly to like 100 degrees. So yeah.
And then related to that, the other question I have is on your gas cycle chart, you mentioned that the gases get cold as they're collapsing. And I don't understand why collapsing gases would get colder. Yeah, your star formation at the bottom of the cycle here, it says gas, cold, and dense. Why does collapsing make it colder? Why would it be hotter?
Oh, okay. So here, as these are collapsing, you would expect them to get much hotter as they collapse. But one of the things that happens once it gets to a certain density, just having only hydrogen alone, you have enough stuff that ultraviolet light from nearby things can't get into it anymore. And you quickly turn from like atomic hydrogen to molecules of hydrogen. And those are very good at shielding even more ultraviolet light. And so as a result, they have a very nice sunscreen for chemistry to happen deep in these clouds. And so you quickly make a whole slew of molecules, which themselves all can radiate away energy.
So it's black body radiating away, and it's just shielded, and that's why it's getting cold.
It's black body with a bunch of emission lines. So it's able to radiate very, very effectively.
Okay, so those will be all the questions. Hello, everyone. So we're going to get the panel started right now. So if you have continuing conversations, can you please take them outside? Matt. Please. Okay. So we'll just start by introducing the panel members. So as I said earlier, my name is Ivana Scala. I'm a graduate student in the department. So things that I specialize in involve stars, specifically, say, the heavy element content of stars and the connection between that and galaxy evolution as a whole. In particular, I like to look at dwarf galaxies.
My name is Mia. I'm also a grad student. I also like to look at dwarf galaxies, and if any of you remember Matt's plot, the one that had like the galaxies that are kind of bad at making stars, really bad at making stars, maybe good at making stars, that plot, like putting all the data into that plot is also what I study.
Hello, my name is Yu Guang, and as two of them, I'm also a graduate student, and my research norm is basically based on the circumgalactic medium, which is basically the gas around galaxies. And I also put on telescope over there because I normally just stand outside. This is my first time doing this panel, so yeah.
Hi, I'm Sarah. I'm a research assistant in the department, and I'm a planet hunter, so I look for planets outside of our solar system.
Okay, so do we have our first question? Yes.
What's the heaviest element that a star like the sun can make?
Okay, so the question is, what's the heaviest element that a star like the sun can make? And it is, they can make elements up to iron on the periodic table. Wait, is that right? Oh, no, that's massive stars. Sorry, I got confused. I thought you said massive stars. But stars like our sun will just essentially make up to helium within their cores. And then beyond that, they won't actually synthesize anything else because the temperatures within the core of the star are not high enough to fuse helium into other elements. So stars like our sun can make other elements in their exteriors once they become more evolved, but not during their normal adult lifetime. So yeah, I hope that answers your question. Mm-hmm. Yes?
So we saw that cycle going back and forth. What if material A is left over that's not turned back into stars? What happens to that extra material, or is it 100% efficiency where everything is all that gas is turned into a star?
Okay, so the question is, in the gas cycle that Matt mentioned earlier during his talk, what happens to the gas that is, not immediately converted into stars?
Okay, yeah. So the short answer, they're still in the space. And if you want a long answer, so actually most of the gas never turn into stars. So what happened to them? So most of the gas actually, not even in the galaxies, they are just in the universe. We call them intergalactic medium, and they are just neutral hydrogen, helium, and not neutral hydrogen. They are ionized hydrogen and helium. And when they are accreted onto a galaxy, they turn themselves into interstellar medium, like all of the gas we see in the Milky Way. And there's a middle point where there's interactions between the interstellar medium and intergalactic medium. Then they are circumgalactic medium, but they are never turned into stars. They are still in the space. Any?
Question in the back? Yeah.
Sure. So the question is that you are interested in what planet hunters do. You would like to know more about what that is. So in our solar system, we have some planets. We've got Earth and Jupiter and Mars and a couple others. But we also, as we learned in Matt's talk, we exist in a galaxy that has lots of other stars in it. And over the past 20 years, we've learned that actually 100% of those stars have planets around them. So what I do is look at those stars that are close enough to us that we can actually detect, either directly or indirectly, the presence of other planets. And so I look for those signals, and then I try to learn as much about the planets as I can from those signals once we've detected them. So, yeah.
So the question was back to that. Okay. Back to the plot that showed the amount of star formation on the y-axis versus the amount of gas in a galaxy. The question was, what happens if you look at another factor, such as the age of a galaxy? And this is a really good question. It's actually an area of active research. We're not, I would say most people are not sure. The vast majority of astronomers would not agree on where exactly a galaxy moves on that plot. Part of my work is to look at other factors, like you mentioned. So it's hard to measure the age of a galaxy, so a lot of times what we do is look at things like metallicity. I don't know if Matt mentioned this, but metallicity to an astronomer, okay, so to an astronomer, metals are anything heavier than helium. So you have hydrogen, helium, and then all the other elements in the periodic table are just metals, which infuriates pretty much everyone, but it makes sense for us. So, so those metals are actually a really good measure of how often the galaxy has gone through this star formation cycle. Because as a star lives and dies, it produces, like Ivana said, heavier elements. And then when it dies, and sometimes as it lives, it releases those back into the environment. So if you measure the amount of metals that are in the gas, in the environment in the galaxy, then it'll tell you roughly how often it's gone through this cycle. Does that make sense? Sorry? Yeah, a bit. Yeah, it's one way that we can estimate sort of the age of a galaxy. And so when we look at metallicity on the third axis, we actually find that there isn't a huge correlation that's obvious in this plot. So we're not really sure what that tells us. It could mean that galaxies at different ages or different stages of evolution still have this. They're still driven by the same star formation processes, but it's not actually super clear yet. This is one thing that a lot of people are trying to answer. Yeah, question?
What's the significance of dwarf galaxies nearby our Milky Way, especially in relation to gamma ray bursts? Let me just rephrase the question. Yeah. What's the significance of studying dwarf galaxies as opposed to other galaxies?
Okay, well, I can answer that it's probably not gamma ray bursts. Those are highly energetic events that I don't think typically come from these objects. Well, yeah, it's useful for that. So a few reasons why dwarf galaxies are interesting. One is that we think that they're very dark matter dominated. That means when you look at what these galaxies are made of, we think most of it is this matter we can't see because it doesn't interact with light as far as we can tell, but it has a lot of gravitational influence on the galaxy. And there's much more of that compared to the actual stars and gas in these dwarf galaxies. For example, some dwarf galaxies don't have much gas at all. So since they're so dark matter dominated, they can be a potential place to look for signatures of direct detection for dark matter, or I guess you would call it indirect detection. Something called dark matter, like if dark matter particles annihilate and things like that. So we haven't made any of those detections yet. Another reason that dwarf galaxies are interesting is from the perspective of galaxy evolution is they're very simple structures. So when you run these cosmological simulations that Matt showed in his talk, making something like a dwarf galaxy is much more simple than making something like a Milky Way galaxy, which has this beautiful and more complex spiral structure. So it's a way of testing our understanding of all of the physics that goes into galaxy formation. Another thing is that the outer regions of a massive galaxy like the Milky Way are made of dwarf galaxies. So what happens is these smaller galaxies are attracted to these larger galaxies like the Milky Way through the force of gravity, and eventually end up being torn apart and incorporated into the exterior parts of the massive galaxy. So clearly the little dwarf galaxies that are around us today, that this hasn't happened to them yet, but this happened at some time in the past with, presumably much more massive dwarf galaxies that have now just become a part of our own.
So just to add a little more to that, so maybe the reason you've heard about gamma rays in conjunction with dwarf galaxies is this dark matter detection. So some people think that if you have, we can't directly see dark matter particles, obviously, but the idea is if dark matter is made up of certain kinds of particles, when they interact with each other, they can produce things like gamma rays. And as Ivana said, because dwarf galaxies are so dark matter dominated, they're a good place to look for these gamma rays. Other places that are really dark matter dominated include the center of our galaxy, but it's also a really busy place. Like there's just lots of junk out there, just swirling around and being hot and doing other things. So it's sometimes more difficult to look for these kinds of gamma ray signatures from places like the center of the Milky Way.
So, comment in the data gallery about the dwarf galaxies and gamma ray bursts. Hi, I'm another grad student. My name's Dylan, and I study gamma ray bursts. So it turns out that there is a specific kind of gamma ray burst that occurs more often in dwarf galaxies. These are called long gamma ray bursts, and they're thought to be the collapse of very, very massive stars. And it turns out that dwarf galaxies are good places for these very massive stars to be born because they're very deficient in these metals that Mia was talking about, right? And so, you get these massive stars and they collapse, and we think that those are what create long gamma ray bursts, and that might be what you heard of as well.
Yes?
Another question about supermassive black holes. I know that there are supermassive black holes. There are different ones. They're different sizes and different galaxies. Does the size affect galaxy formation? Like if one is bigger than the other one?
So the question is if the size of, I guess you mean the central supermassive black hole impacts the galaxy as a whole.
It's actually a very good question. So there's a relationship, we call it M-sigma relationship in astronomy. It's basically when you have a massive galaxy, it tends to have a very massive black hole. And when you look at that correlation, it's actually a very tight correlation. So what people take away from this, there are two ways to interpret. One thing is that so basically when you form a supermassive black hole, you need to accrete stuffs onto it. So stuffs need to fall into there. And then the supermassive black hole, when they eat stuffs very much, it tends to have that the similar feedback of star formation. They tend to have feedback to have strong emission to the stuffs around them to push away them. And we call this stage as an AGN or quasar. They're active galactic nuclei. And so this tells us that the accretion of supermassive black hole actually regulates itself. So when it eats too much, it starts to stop. It freaks out. Yeah, and then it also affects the accretion of the gas onto the galaxies. So because the supermassive, the AGN and quasars are very energetic, so it also stops the accretion onto the galaxy. So that's they have like co-evolution. They grow at the same time and they stop growing at the same time. The other interpretation is that if you want to form a supermassive black hole, you also need to have black hole mergers. And so when you start with random distribution, a random mass of galaxies with random mass of the supermassive black hole in the center, when you have like tons of times of merging, eventually they will be just have a tight correlation. When they have more mergers, they have more massive supermassive black holes. So yeah.
Did that more or less answer your question? Yeah. I will say that it is both of the things that Yuwang talked about are still open areas of research. So the ways that central supermassive black holes act as engines producing feedback, which is just injecting energy into its galaxy, we're not actually sure what those mechanisms are. A lot of people talk about things like jets, but it's still not super clear. Probably has to do with magnetic fields. And then the other thing, how black holes merge together, this is a really, really big question because a lot of times we see in very early galaxies, so galaxies that are quite young, we see them at the time when the universe was very young, like a couple million years old, and we already see that they have really big supermassive black holes. So the question is, how do you build up to these giant black holes so quickly? No one really knows. So, good questions. Yeah.
And just to add, the problem with feedback is that the supermassive black holes are just so energetic. So if you count all of the energy it emits during the quasar process or the aging process, the energy it emits can potentially blow all of the galaxies away multiple times. So the problem is how many energy really impacts the galaxies around them. So that's an open question. No one really knows.
Yeah, so what he's saying is that the energy that the black hole injects into its surrounding environment, is it mostly directed away from the galaxy rather than, say, the plane of the galaxy if you're dealing with something like a spiral galaxy like the Milky Way?
Yeah, so there are a couple different ways that a central supermassive black hole can inject feedback. So the jets are one way. Another thing they can produce is a lot of radiation pressure. So there's all this stuff falling into the black hole, and it's heating up as it's falling in, and as it heats up, it produces energy. And a lot of that energy light from, how do I put this? The energy from that can actually help push things away in all directions. So that's one option. I think there are a couple of others. We just covered this in one of my classes, and I've completely forgotten. So Yuwang's going to take it.
Yeah, so, I think the mechanisms you summarize are there are two normally mechanisms that are called AGNs. One is just the jet that Mia just mentioned, and the other one is just, we call them quasars, are just radiation from the accretion disk. They are in all bands. They're in all electromagnetic bands. So ranging from optical to infrared to radio to X-ray. So they are very loud. They are very energetic. And whether it has a preferential angle to inject their radiation to some certain stuffs, that's definitely true. But at what degree, that's also an open question. So people really know that there are multiple types of AGNs. For some of them, they are very bright in optical. For some of them, they are not. They actually look just like a normal galaxy if you don't take a spectrum of them. So that means some of the light are blocked, and some of the light we can see them directly. So there is definitely a preferential direction.
Oh, yeah, question in the back?
Yes, it's about theory. In trying to explain how stars form, this is the current theory. Has this been the current theory for 20 years, 2 years, 4 years? What's been the battle over this theory? Is there some preceding model for how these things happen? This one is not being very confident? Or do you guys know what the
Okay, so the question is regarding the history of our understanding of star formation. So is the model, that Matt presented during his talk and that we currently accept the model that we've accepted, say, for the last, 20 or so years?
So that's a really good question. This law between the amount of star formation and the amount of gas, that's been postulated since like 1969 when some guy named Martin Schmidt, who was here at Caltech, I think, yeah? He's still here at Caltech. My bad.
You can't see him, but if you just go into there's a restaurant he normally goes.
Oh, there's a restaurant, okay. I don't know if you heard that, but Yugong said there's apparently a restaurant Martin Schmidt goes to, which I did not know about. Anyway, so he postulated that like back in 1969. And then in 1998, this guy named Rob Kennicott, who is kind of like an Arizonan Santa Claus, in that he's from Arizona and he's very jolly. He was the one who actually put together most of those observations that Matt showed. And he's the one I work with on a lot of this stuff. And that was back in 1998. So since then, it's been 20 years. And the theory behind these observations has in fact changed pretty drastically. At one point we thought that, so Matt has sort of described these giant clouds collapsing, and then the individual properties of those clouds, so like for instance the density of the gas in those clouds affecting the star formation. Back in the 60s it was kind of an open question whether it was the internal properties or the big external properties of the galaxy. So not just how much gas you have in a place, but whether or not the galaxy is rotating quickly or slowly, if that's helping things collapse, that kind of thing. And so you sort of have these two different pictures, like this top-down picture where the bigger properties of the galaxy are helping drive things, or this bottom-up picture where it's these individual clouds that are driving things. I would say at this point most people tend to favor this individual picture of star formation, but it's still pretty clear that galaxies as a whole do affect star formation. And so that is one of the things that I think Matt is working on. And Ivana.
Yeah, so I think our picture of how star formation proceeds as a whole and perhaps on larger scales is something that hasn't changed much, over the last 10 or 20 years or something like that. But what are still active areas of research are the details, when you start getting down to small scale. So one thing that Matt looked into using these simulations that he showed earlier was when you have star formation occurring, whether you have in these gas clouds fragmentation, which is the breaking up of these gas clouds as it collapses occurring first, or if you have this self-shielding that he mentioned occurring first, which is where the cloud itself makes it become opaque, essentially, to radiation. So I don't remember what the conclusion of his research was, admittedly, but but he certainly came to one. So that's just an example of some of the research that is actively being done. People study something known as turbulence a lot, which, is a very messy process and is important in driving, inside clouds of making certain regions more dense than other regions, and then ultimately resulting in things like gravitational collapse.
So one of the open areas of research in planetary science or exoplanetary science nowadays that kind of relates to the tail end of your question is how planets form. So before we discovered exoplanets, we only knew about the planets in our solar system. And we saw a general trend that we had smaller rocky planets that were closer to the sun, so like Mars and Mercury and the Earth. And then we had giant kind of puffier planets like Jupiter and Saturn that were a little farther away. And then we had icy bodies that were even farther, like Uranus and Neptune. But some of the first exoplanets that we discovered really didn't fit this kind of general idea, and they posed a major challenge to our theory of how planets form. So for example, some of the first types of planets we found were planets called hot Jupiters, which were giant planets that were even bigger than Jupiter, that were orbiting closer to the sun than Mercury is. So these were really, really oddball planets. And our used to be understanding of planet formation couldn't really accommodate this. So people are actively in exoplanet theory now working on how planets form, how giant planets like this can get close to their stars, whether they form where they are or whether they kind of migrate in over time, or if there's some alternate theory of planet formation that maybe certain planets form more like mini stars rather than like, pebbles kind of like accreting and bumping into each other and building up into planets over time.
There is, we will let you continue to ask.
So we're odd. Our solar system's odd. We're not orbiting.
It's hard to answer that question currently because the types of planets we can find are subject to lots of biases. So there are different methods of looking for planets, and they each preferentially find certain types of planets. So right now we don't have the capability to see like every single planet in our solar system without biases. So it's hard to place some constraint on whether our solar system configuration is rare. But we can say that planets that are the size of Earth, meaning that their radius is the same as the radius of Earth, are common. We don't necessarily know whether planets that are exactly like Earth are common, but we're getting to, stay tuned. We're going to figure this out in the next couple of years, hopefully.
Kind of maybe half answer, but right at you said that the first exoplanets we found were those giant Jupiters, which are close, which is unexpected. But then I guess we can't find everything. Our techniques will probably maybe tend to, well, those are the easiest things we can find. And so maybe we're kind of biased that we found easy things which maybe are even rarer. And so it's kind of, maybe all kinds of things happen out there. And so we just have to see these very unusual things and we just can't see the more normal things.
Yeah, so the statement/question was that probably what's happening in exoplanets, which is true, is that we're finding the things that are easiest to find with the current detection techniques. And so we might just be seeing things that are actually kind of rare, but that are just kind of the tip of the iceberg that are easiest to find. And people do a ton of work in exoplanets trying to figure out what these biases are and statistically characterize them so that we can say, this is not just the number of planets that we found, this is actually the rate of these planets in the universe corrected for all of these selection effects. So we still can't say anything about the areas, the types of planets that we're unable to see with our techniques, but we can say, like, within a certain amount of error and uncertainty, like, this is the actual rate of these planets. So we know, for example, that giant planets that are far out, like more than Jupiter size, that are kind of outside of, even outside of where the giant planets in our solar system are, we know those types of planets are rare. But planets that are giant but closer than they are in our solar system are more common. And we can say that with some certainty.
So the question is, how many different sources of measurements are used in astronomy, I guess?
No, not how many different, but could you just describe what is being, just generally like, okay, I don't want to say specific words because I'm trying to figure out. Like, okay, for example, one source of information might be the telescope over there. Like, we can go over there, look in the telescope and see things, and then like write things down. And that would be like a source of information. Like X-ray, radio. Yeah, like different types of light.
Yeah, so
Like, is it all light, or is it like, I mean, maybe there's not, maybe there's sound, or maybe there's no sound in space, or like, can you just, and what tools are used to collect the information, or most of the tools in space are on the ground, or like, when you're actually kind of testing your theories, like, where, like, I mean, the simulation is one thing, but then, like, you want to kind of also kind of check to see what's going on. So, like, I just don't have a sense of like, okay, 70% is this kind of stuff, 30%, or just really.
Okay, so I would say that until very recently, every single astronomical observation was based on the light that comes from things in space. Until last year, 2 years ago, oh God, I don't know, time doesn't exist anymore. 2 years ago, there's, okay. Yeah, okay. Well, we're not gonna, okay, until very recently, almost all of the information came from light. Some of it came from neutrinos, which are particles that are very small. They're probably streaming through all of our bodies right now, but we can't feel them. They interact very rarely. And then 2 years ago, we discovered gravitational waves. So we found that the interaction of bodies in space can actually produce bending of space-time that we can measure. And those are gravitational waves. Most of the observations that I think everyone here works with are light. So I can briefly describe some of what I do. So to do measurements like the ones that Matt talked about in his talk, I mostly use images in different areas of the electromagnetic spectrum. So the electromagnetic spectrum goes all the way from gamma rays, which are the highest energy and the shortest wavelength, to radio waves, which are the longest wavelength and the lowest energy. And I particularly look at images in the infrared, which is just to the red end of our vision, and then the ultraviolet, which is just to the violet end of our vision. And I use those images to basically count how much energy is coming out from galaxies in different wavelengths. And from that, I can tell things like how quickly is it forming stars, the amount of star formation, what kind of gas, well, not what kind, but how much gas is in a galaxy, that kind of thing. For that kind of work, I use what we call photometry, which is basically taking an image, drawing a circle around parts of the image, and saying how much light is coming from that part of the image. Does that make sense?
Yeah, and so they could come from, those images are coming from just telescopes on Earth, or
yeah.
Or it doesn't matter, or most of them are coming through.
Yeah, so there's a mix. Here at Caltech, we have access to several different telescopes. We have the Palomar Observatory, which is like 2 hours from here? I don't remember. I think I slept for most of that drive. 2 to 3 hours. We have Mount Wilson Observatory. They still do some optical interferometry up there. And then we also have access to a lot of telescopes in Hawaii, the Keck telescopes, which are both on ground. Radio telescopes. There's the Owens Valley Radio Observatory, which is near Bishop. We have other stuff. We have a lot of collaborators around the world too, so we get to use telescopes that are located around the world. And some people here do use telescopes in space, such as the Hubble Space Telescope and, fingers crossed, eventually the James Webb Space Telescope, which may or may not be coming to a sky near you sometime in the next, who knows, it's supposed, anyway, okay. Yeah, and then Ivana uses different kinds of data, which she will talk about now.
Yeah, so I'd like to emphasize that the method that you use depends, one, on the type of light that you're looking at, but also it depends on how distant the objects that you're looking at is. So what I look at are very nearby galaxies, where I can actually see the individual stars within these galaxies using large ground-based telescopes, such as the Keck telescopes in Hawaii. So I can get individual spectra, the flux as a function of wavelength for all of these stars that I'm looking at, and learn from them that way. But everyone doesn't have this privilege, if you would call it that. Depending, if you look at a galaxy that's farther away, you can't see its individual stars. So you can get a spectrum for, say, the entire galaxy as a whole, where you have, and that looks very different from the type of light that you would see from an individual star, and contains different information, because it's, again, the stellar population of the entire galaxy. You can also look at, photometry, which is just where you're not doing spectroscopy, which is when you're separating it into how much light do I see at a certain wavelength for a galaxy. And then you can do kind of draw little pixels in the stuff on galaxy and look at light in different sections of it. And then you do more high redshift observations, right?
So just to generally answer your question first, is that this question is really a broad question, and I would say if you want to take it seriously, it was like a whole year of curriculum in a college. Yeah. And yeah, seriously, because we have like the detection method of astronomy is so complicated that we basically use all of the ways we can find that's practical to use to study the space. And what kind of detection methods you want to use really depends on what kind of science you want to do. So we just went through 2 subjects, like what we do to study the space, what we do for what detection we use. And so for me, I study very distant galaxies. Those galaxies are very far from us that we don't really have the privilege as Ivana's galaxies do. We can't resolve them to individual stars. So what we do basically is the same. We use spectroscopy on Keck telescope because Keck telescope is basically the most efficient telescope on Earth. So they are very capable of observing those faint objects because they are very far. So they tends to be extremely faint. And if you want to do the observe the spectrum of them, you need to disperse the light, so that only makes them much fainter, only makes them much more difficult to observe. And so the way we do is that we put a galaxy into our spectrograph and we disperse the light and take like 2 to 3 hours integration exposure. And then we have a very faint spectra. To be honest, if you untrained people, if you take a look at those spectrum, you don't recognize anything. They're just random stuff. And sometimes we see there are spectral lines in them, and we see spectral lines in emission, we see spectral lines in absorption, and then we can use those spectral lines to study the kinematics of the galaxies. Like what I do, I study the kinematics of the gas around galaxies. So, yeah, that's it.
So I guess I'll just jump on this bandwagon of co-opting your question to talk about what I do. So I think the field that I work in, exoplanets, is a really great kind of playground for astronomy because there's lots of we use light in lots of different really innovative ways to learn things about planets. So I'll give like a couple of quick examples of like the types of technology you use and the way that you interpret the light that you get from stars and planets. So the first way, which sounds like the most obvious, but is actually like the most technologically difficult and actually only developed in the past couple of years, is directly imaging planets. So it's exactly what it sounds like. You point your telescope, which is just a giant camera, at a planet, and you see if you can take a picture of the planet. The problem with this, and the reason it's so new, is that stars are really, really, really bright, and if we're looking at something that's really far away, like a star, and a planet is orbiting pretty close to the star, the planet's light gets kind of lost in the light of the star. And the analogy that people usually make is that it's like trying to find a firefly next to a torchlight from a distance of like a mile away. So like really can't see it with your naked eye. So we've developed this really cool technology called coronagraphy, which is basically just putting a little block in front of the star so that the light from the star doesn't actually get to your telescope. And a lot of complicated engineering happens, and you can tease out the light from the star you can distinguish it from the planet. And that's really cool because getting the light directly from a planet and not like indirectly observing its effect on a star allows you to do what these guys were talking about before, spectroscopy. And so spectroscopy is a fancy way of getting the chemical abundances of something, so you can figure out what a planet is made of by looking at its light directly. Another way that we use light in exoplanet studies is by observing stars and looking for indirect effects of planets on their host stars. So a really famous mission is the Kepler mission. So this is a space-based telescope, so something that's orbiting, and it stares at a bunch of stars and looks for dips in the brightnesses of the stars that occur when the planets pass in front of the stars. So if your star is there, the planet kind of passes between the star and you. And we can't see the planet passing in front, but we can see the brightness of the star go down a little tiny bit because this dark planet is blocking out part of the star. And so we look for those dips, and we can eventually, if we see enough dips, we can figure out properties of the planet. So it's cool.
Yes? Oh, so the question is, how do we simulate a galaxy? So this is something that we do using really powerful supercomputers. The reason that the computers need to be so powerful is because, as you can imagine, galaxies are extremely large and also complicated systems. And you need to be following the evolution of a bunch of different, stellar populations at once and a bunch of different gas clouds at once. So when we make these simulations, we write them all using programming. So we use programming languages in order to tell the computer what to do and what kind of calculations to make. We include information about, gravitational interactions. For example, you have these two gas particles or, large gas clouds next to each other in these simulations, and they're interacting in this way gravitationally. And if you have a stellar population in there, you also have it interacting radiatively or through light with the surrounding areas. So you're, based on our knowledge of physics that we essentially program in those equations, you're solving these at every single time step. You start very early on in the universe, and then you make the calculations, you move forward in time. And then you make the calculations, and you keep on doing this until you get to present day. Yes, most definitely. So the question is if we are coding in the laws of physics into these programs. Do you mean to cool them down? I don't think they usually use water. I think they usually just keep them in a very well air-conditioned environment. I have used supercomputers, but I don't go visit them in person, although I should. Okay. Do we have any other questions? Do we have one over there? Or is your hand just flying up? Yes?
I had a question about planet formation. In the studies of exoplanets, did you guys figure out a rule of thumb for how many sort of generations of star formation and explosion and reformation like a star has to go through before it forms planets, before the velocity is high enough?
That is an interesting question. So this is probably a question that a bunch of us here can actually help answer, because what I know is the types of stars that planets form around. I don't actually know a lot about how those stars get to be where they are. Does anyone answer that question?
So the very first stars, as far as we know, were composed almost entirely of hydrogen and maybe some helium. And then over time, they built up heavier and heavier elements and then eventually expelled those. So the next generation had heavier elements of stars. And we call those, the very oldest stars, population 3 stars. And then the most recent stars are population 1 stars. I know, it's backwards. What are we going to do with the next generation of stars form? They're going to be population 0. It's going to be terrible. But yeah, I think it's very unlikely that population 3 stars, because the universe was mostly hydrogen and helium when these very first stars formed, there wasn't really any other elements to form planets. I think they needed to be old enough. The stars needed to be at least second or third generation stars at that point. Does that kind of make sense? I don't know.
So the reason I'm having so much trouble answering this question too is that it's still a very open area of research, like what types of planets tend to form around what types of stars and the relationships between stars and planets. Like I alluded to before, we don't still really understand how planets form in the first place. and we don't even have like a large enough sample of different types of planets to be able to say anything really definitive about planet formation. But that said, we do imagine that there have to be certain conditions for planets to form. Basically, like the star has to be like calm enough for the planets to survive. So if there's like if there's a lot of like forces on the no, I'm not gonna. We have no idea. Yeah, the other issue is that we can only see planets around stars that are in population 1 that Mia talked about. We can't really, our galaxy simulations that you saw Matt talk about today don't really have the ability to simulate planets yet. They just simulate like blocks of stars, not even like individual stars for the most part. And so it's kind of unclear how planets fit into this whole like larger picture of like where in the galaxy they form. I think this is going to be a really exciting like area that's going to open up in the next couple of years, like where planets are distributed among our galaxy, for example. So one, just to like keep talking, one like exciting thing that's happening very soon in the next year actually is the launch of the TESS missions. This is a transiting exoplanet satellite survey, right? Michael? Survey? I don't know. Transiting exoplanet something. That works. So this is a satellite that's going to launch and is going to look for planets around the entire sky, which is kind of the first time that we're going to have a really large-scale survey looking for planets not just in one part of our galaxy. So we're going to be able to do kind of like galaxy archaeology with planets, try and figure out where in the galaxy planets tend to form, if certain parts of the galaxy tend to form different types of planets than other parts of the galaxy. So, I know, right? This is like, everyone should go into exoplanets. It's the best field ever. Several thousand. So there, I don't know if it changes every day. But the transit method that I talked about before, which is looking for the periodic dips in brightness that are caused by a planet passing in front of a star, that's the most successful method. So that's found several thousand systems on its own. And then the next most successful is the radial velocity method, which looks for the gravitational tug of a planet on its host star. So that's the second most successful. I think that's found about 1,000-ish. I'm actually working in radial velocities now, so I should know, but I don't. And then, okay, cool.
I checked last week and there were about 5,000 exoplanets currently found. So.
Do they, so I'm sort of not buzzing, so do they have a goal for how many more they want to find with the
As many as possible, as many as we have like money to find, basically. To kind of answer that question a little bit better, like the field has now moved from just like trying to find as many planets as we can because every new system is exciting, to trying to find planets that fill in our bias gaps. So we want to find systems that are different, systems that are hard to find with our current methods to kind of build a more complete understanding of the population of exoplanets, rather than like just that. So that'll help us answer questions about like planet formation, for example, and other open questions.
This is sort of a follow-up. You said that the transit method is the most successful method, but it seems like just because the odds of the planet actually including part of the star are so minimal because of the just the odds that it's going to be pointed that way toward the ecliptic plane of their orbit could be facing us. It seems like in all cases you see some wobble. So is it just that the ability to detect the wobble is so much weaker than your ability to detect the hit and light?
That's a really good question. So the question was, why is the wobble method not more successful? Shouldn't it be easier to detect like wobbles due to gravitational interaction rather than these tiny blips? And on top of that, there's this geometric effect that you said that they have to be right along your line of sight for these planets to be found. And the main answer to that is that these wobbles are really hard to detect because planets tend to be much, much less massive than their host stars. And an issue that we're running into now is that we're getting pretty good at detecting planets, but stars actually produce their own kind of like wobble-ish signatures. Stars do all sorts of weird things like expand and contract, and like they have star spots that are like sunspots, which are just like areas of really intense magnetic activity that can kind of almost look like planet wobbles. And so all these kinds of like noisy effects get kind of reduce our ability to detect planets. We have similar issues with the transit method, but it turns out that there's noise effects in both cases. And the transit method is the most successful because of the Kepler mission. So we've had a specific mission that just looked at a bunch of systems and found a lot of it, just got really good at what it was doing, basically. Radial velocity is starting to hit its stride, but yeah, transit kind of stole the show.
So do we have any more questions? Yes? Yeah. Oh, okay. So we're not going to collide with Andromeda for a long time, thankfully. We still have at least 4 to 5 billion more years before that happens. So that's about as old as our sun currently is and our planet about, so so what is ultimately causing that though is just the force of gravity, the same force that's keeping us here tethered to our own planet. The force of gravity working on these really massive galaxies over the course of billions and billions of years will ultimately bring the Milky Way and Andromeda together. But not for a while.
Oh, we have a poster for you. Does anyone else have any other questions? Well, wait, yep. All right, so the question was, for each of us, what would be a great breakthrough in our particular field of research? Like, what could be the next big thing? And I'm going to give this mic to anyone who's not me, because that is a good question.
Aliens. So a lot of exoplanet hunters have a kind of interest in life on other planets. We think that the most likely place that we're going to find life in the universe is on planets, because the only place we know in the universe that has life is a planet, this one. And people are looking both in our solar system on other planets, like on Mars, for instance, and also we're kind of like slowly developing the tools that we need to look for like chemical signatures of life on exoplanets. So discovering alien life would not only like give my field enough money for me to retire happily, but it would also, it'd be so cool, right? Like if we found aliens, like, yeah, that'd be sick.
Yeah, all right, so I guess the ultimate question we want to answer for my research is that we want to explain the formation of galaxies. So as I just said, the galaxies form by accreting stars, and they regulate their accretion rate by doing feedbacks onto their gas and onto their stars. So the way of doing that is the way of studying how galaxies really form how they like regulate themselves, what causes the regulation, and how strong they can do to their surroundings, one way is to study the circumgalactic medium. It's the gas surrounding the galaxies themselves. And because the circumgalactic media are basically a place where you can have both stuffs happening, it's basically a place where galaxies talk to the universe. You can have the gas from the universe to be falling onto the galaxies, which feed their star formation. And you can also have those outflows, those feedbacks being pushed out from the galaxies. So studying the circumgalactic medium is a way to really look into the details of how galaxies are formed. And I guess a major breakthrough in our field will be one day that we can really answer all of the questions regarding the galaxy formation.
Okay. All right, so this is going to sound really boring, but hear me out and it will be useful. So I think that would be really cool is if somebody could just tell me when a group of stars form, what masses do they form at? Because no one knows. We have a lot of ideas. We have some evidence that in the nearby universe, most stars are when they form initially, are low mass, and we only get a few of the higher mass ones. But the exact numbers are still really uncertain, and especially when you start including things like binary stars and systems of stars, and it gets really complicated, and definitely no one knows the answer to that. And this affects pretty much every area of galaxy studies that I've ever worked in. Every single paper at some point they say, we assume this kind of function. And if those are wrong, then that would be great. I mean, it would be terrible for pretty much everyone, but it would also be great because we would actually know for sure, and that would be amazing. So, yeah.
So in my field, what would be excellent is if we achieved a thorough understanding of galaxy formation also, but specifically relating to our understanding of how structure in the universe forms as a whole. So what I do when I look at these nearby dwarf galaxies is I look at their stellar atmospheres and try to learn about their chemical compositions. And learning that type of information about these galaxies, I can compare it to things like the massive galaxies like Andromeda and the Milky Way and see how they're different and how they might be similar. So, for example, if we look at the outer regions of the Andromeda galaxy and we notice that it has these very specific chemical signatures, and we would be able to definitively show that these chemical signatures correspond to more massive dwarf galaxies that you would find earlier on in the universe, we can definitely say this is how you build up this galaxy and this is how structure formation proceeds in our universe, and that this is in support of the entire model that we have for the universe as a whole. So, which is known as the cold dark matter model, essentially, where you have these galaxies forming inside of these large blobs, essentially, of dark matter, and then larger galaxies gobbling up these smaller ones. So we do have a fair amount of evidence to support this, but it's still something that we're always actively testing. Yeah? Okay, so the question is if there could be hollow planets.
So I want to preface this with anything is possible. Given everything that we know about the way that planets form and the way that gravity works in particular, we don't think there probably wouldn't be. But I don't know. I mean, we've been completely wrong about everything we've known about the universe before, so it could totally happen again. But the kind of like physics justification for why that wouldn't happen is that gravity tends to pull things together that have mass. And when you have a spherical object like a planet, most of the mass tends to be pulled towards the center. So our idea, or canonical idea of how planets form now is that stuff sticks together over time and that stuff grows from the inside out. And so we think that the most massive, the most weighty stuff is at the center of a planet. So it's a little bit more difficult to imagine a scenario where you'd have lighter stuff at the center and heavier stuff on the outside, but I don't know. I'll let you know if I ever find one.
So there's a mass limit. So if you make assumption that all of the planets, well, most of planets have composition that's similar to the planets in our solar system, so there's a mass limit. When you reach a certain mass, the stuff tends to be just sphere. So when you look at those meteors or comets, they tend to be very irregular because they are very less massive, and they don't have enough gravity to pull them into a sphere. But who knows, maybe planets can be made of strange materials, maybe, I don't know.
Are there any other questions? Oh, yeah.
Yeah, so when you mentioned that one of the sort of interesting breakthroughs that might happen would be like finding life somewhere else. What is life then? What criteria would need to be met in order for that to occur? And of course, this is probably a discussion about this, but just what are some things that people throw around?
Sure. Yeah. So, like you said, and like I'll repeat, this is something that we have no idea about, and we haven't even like really started to like define yet. And it's also, I'm going to first give a really boring statistical answer to your question, and then I'll give a more interesting answer. But the boring statistical answer is that we have a sample size of 1, meaning that we know of life existing in one place, and all the characteristics of the probability distribution defined by the sample are undefined. So we have no idea like what the standard deviation of our characteristic X of life is. So we have no way of predicting like where life might be or what life would look like, whether it would be similar or different to life on Earth. And the more interesting part to the question is that we can't even really reliably define life on Earth. So we're going to have a heck of a time defining life if we find it ever somewhere else. But some things that people talk about are biosignatures that we would be able to see in the chemical composition of a planet. So in this imaginary scenario, we've got a lot better engineering in the future, and we can actually detect a spectrum of a planet that's very similar to Earth. So we've gotten a bunch of like kind of orthogonal measurements that give us the mass of the planet, and we say the mass is similar to the mass of Earth, and we get the radius of the planet, the radius is similar to the radius of Earth. We point our telescope at it, and we get a spectrum which tells us about its chemical composition. We would look for water first. We would also look for oxygen and a bunch of other things like that. Now, there's a lot of discussion about that because oxygen could also be caused by volcanoes and like lots of other stuff. And so what you'll actually see happen when we discover some biosignatures like this on a planet that is similar to Earth is that scientists are going to argue about it endlessly for like 15 years until we actually like make contact with whatever's on there, and we can be like, oh, there's really aliens there. But the other thing I was going to say is that I went to an interesting talk the other day about how we would detect mountains on planets. So this is a kind of building off of the geometric or the shape of the dimming of the star's light that you would see in a transit event. So if a planet passes in front of its star, you see the dimming of the brightness, and the shape of that brightness curve over time has a characteristic shape. And in the future, if we get really, really good like transit detection machines, we actually might be able to see like if a planet is rotating as it passes along the surface of the star, we could see like characteristic things that could tell us about like the size of the mountains on the planet. So that doesn't really have anything to do with life, except maybe like we know that there could only be mountain goats or something on this planet. But that was also kind of a cool like future-y thing that I wanted to tack on the end of that question.
Any more questions?
exciting topic. I'm sorry. Sorry, not sorry. Another thing that people are doing is looking for radio signals from intelligent civilizations. So there are actually a couple of concerted efforts for specifically doing this, like just pointing radio telescopes at the sky and looking for like radio transmissions from ET, basically. So these would have to be really, really well-evolved aliens that had pretty amazing technology, actually better than the technology that we have. If we were trying to detect us, we wouldn't be able to, so they have to be smarter than us. But yeah, we're looking. So if we get like some very distinctive radio telescope signature, radio transmission signature from a localized place in the sky, like not from the whole sky, there would be a lot of excitement, and you would read about it in the New York Times, and we would try and do some other follow-up stuff. So that's another potential, less likely way that we could find aliens, is by communicating with them. But that'd be sick, too.
Right, there's a question. So the question is how the galaxy formations are related to planets formation.
Okay. I'm sorry, I've been talking a lot, but so the basic answer is that we don't think that we can have planets without stars. So if galaxies are bad at making stars, then they're probably pretty bad at making planets too. But there are some kind of like caveats to that. We have found a few free-floating planets that are not actually orbiting any star. We found several more free-floating, what are called brown dwarfs, which are in between the size of planets and stars that are not orbiting around a more heftier object. And we think that planets and brown dwarfs might kind of be related, and it's really hard to find kind of free-floating small planets. So it might be that there are more out there that we just can't see. And exoplanet hunters are kind of puzzled at how these planets form. We wonder if they form the same way as stars do, if they kind of are collapses of cold gas, or if they're like planets that have been kind of kicked out of a system where they were born with other planets and a star. So theoretically, if I think that the answer is that you probably need stars to make planets, but in the kind of what if category, maybe there's some alternate way of making free-floating planets that we don't really understand that could, it's not likely, but maybe. Okay, so the question was, how does the presence of heavy elements impact planet formation? We think that heavy elements make it easier to form planets. So the more heavy stuff you have, the easier it is to attract other stuff and kind of build up the planet. So we're starting to see an emerging relationship between planet size and metallicity of the like disk where the planet forms, for example. So if the birthplace of the planet is more metal rich, it'll be easier to form, we think, more massive planets. And if it's less metal rich, then it's harder to form more massive planets. So it might be that we need to have lots of metals in order to make planets. Does that answer your question better?
I'd like to add something, is that, so there are theories predict that the first generation of stars may be very massive, much more massive compared to the stars that we see around us. So massive stars tends to evolve really fast. So maybe the first several generations of stars maybe just dies really fast in just a few billion years after the Big Bang. But those are just theories. We can't really see that. We can't really say that's true until we see evidence of that.
Yeah, so back to the life thing, but a different angle, more of a galaxy angle than a planet angle. So we heard that, I heard that one thing that people like to do is look for stuff that's similar to Earth, kind of planet or whatever. But also people talk about like how like Earth is like a Gaia type thing, that Earth is like one big organism or something with the interconnectedness of life, and that there's kind of cycles and so on and so forth. So and for example, in the metaphors that you use when you speak of it, like the birth and death of stars, and maybe for galaxies too, and so on. So like, is there a sense? Do you think of is that kind of Gaia metaphor, like the analogy from like a human kind of thing to planet Earth, or looking for life on another planet, to thinking about life as kind of maybe kind of on a star level? Is that something that you think about at all, or is that?
Okay, let me see if I can break down that question. So part of the question was asking if we think of galaxies and stars sort of in the same way that we do planets. We talk about the birth and death of them. We talk about how they interact with their environment, that kind of thing. The connection to life I'm not too sure about, but I can at least answer that first part, which is that we definitely think of galaxies as environments. So they're not just environments, but environments that are actively interacting with other galaxies, with the environment around them. So I don't know, you can think of stars, individual stars, as a forest, as trees maybe. So the tree is born and it lives and then it dies, and when it dies it gives stuff back to the forest in the form of composting, I guess. And then the galaxy is like the forest as a whole. So there's stars in there, but there's also a lot of other junk in there, and also the things that happen outside the forest affect what's in the forest. Does that kind of make sense? So galaxies in that way you can think of as these really big open systems that have a lot of really complicated interactions. I think that's maybe, I don't know if that's answered the first part of your question. Okay. Okay, yeah, cool. Yeah, Sarah will add things.
So I don't know if this is related to your question at all, but one theory that people kind of toss around sometimes is a theory that life could travel between planets via like meteorites or asteroids, and so there could be some sort of organic molecules on one planet, and say a large body collides with that planet and breaks off this piece with these organic molecules, and that could be transferred to another planet where it generates into life. So some people think that that could be how life formed on Earth, that it was originally on Mars and that a piece of Mars broke off or somehow was transferred to Earth and those organic molecules formed. There's not really evidence for that, but people talk about kind of like a inter-solar system spread of organic molecules as being possible, at least.
Don't they find a lot of kind of complicated molecules just in gas galaxies anyways? So that a lot of surprisingly complex molecules actually form just in space.
Yeah, so people do find that organic molecules can just form out in space and interstellar gas. So it seems like the building blocks of life itself are not that difficult, to just naturally form within clouds and the like. And you find very complex molecules out in space. I don't know the details of which organic molecules specifically, but they're out there.
Yeah, so there's a really big community of astronomers who basically do nothing but study dust. It turns out there's a bunch of these really complex molecules just sort of floating around in space, doing whatever it is they do. And they have huge takedown arguments, well, okay, I haven't actually seen any of them fight, but they get really intense about dust. And in particular, one thing that they look at is what they call PAHs, polycyclic aromatic hydrocarbons. So hydrocarbons, as you might have guessed, are made up of hydrogen and carbon, which happen to be the building blocks of life are carbon, hydrogen, oxygen, nitrogen, and other stuff probably. But Yeah, so that's sort of a more specific example, I guess, of those kinds of really complex molecules that are just out there. Yeah. Any other questions? Yeah?
Are globular star clusters considered like population 3 or 2 stars? And are they more efficient at star formation versus galaxies today, like the pinwheel or spiral galaxies?
All right, so the question was, are globular star clusters old or young stars, and are they more or less efficient, were they in the past more or less efficient at making stars? Does anyone want to take that?
Like, I thought they were like an ancient structure of a like a primitive galaxy, in other words.
Yeah, we do think they're old.
Yeah, so globular clusters do tend to be very old objects, and for that reason, very poor and heavy elements. But they're distinct from galaxies in that one of the ways that we distinguish galaxies from globular clusters is the fact that they have enriched themselves through multiple stellar generations. So, you know, when you first look at a globular cluster, you're like, it's a collection of stars that are self-bound to one another through gravity. You know, how is that distinct from a galaxy? But all of those stars tend to have the same amount of overall heavy element content. You know, there was, you know, one burst of star formation that formed the cluster as a whole, and then after that it ceased. Whereas in a galaxy, again, you have star formation proceeding for billions of years, you know, in some cases. So, and then as that's happening, right, you keep on having more metals produced, and each next generation becomes more and more enriched. So that's the most, I would say, important distinction between them. But globular clusters are an important part of galaxies overall. Okay. So do we have any last question? We are pretty much out of time, but we could take one more quick one. Yeah, okay. If not, then thank you very much for coming. I hope that you enjoyed the night.